There is a whole state of matter that pretty much most people are unaware of. We're all familiar with solids, liquids, gases, and most of us in the world of science know that plasma is considered the fourth state of matter, but in fact, there are actually more states of matter. In today's video, I'm going to talk about one of these new states of matter, the Bose Einstein Condensate. Now, this is a particularly weird state of matter because it's very hard to imagine, and it's a highly quantum effect which is only visible at very, very, very specific conditions. These conditions are that it can only happen with bosons, and also the temperatures must be incredibly low, like we're talking a few degrees above absolute zero. They can also only happen at very low densities, something like 1/1,000,000th of the density of normal air. But how do these gases form Bose Einstein condensation? Well, we're going to be using some of the knowledge in the previous video, particularly looking at the Bose Einstein distribution. And we're going to be using that to see how we can derive this effect that we observe at very, very low temperatures. And believe me, this effect is really cool. It's like quantum mechanics, but happening on a macroscopic everyday scale. It allows you to see wave functions. So without further ado, let's jump into it. So in the previous video, we derived the Bose Einstein distribution, and that we said that the average occupancy of a state K, of a single particle state K, is equal to 1 divided by e to the epsilon minus mu over kBt minus 1. And this was the Bose-Einstein distribution. And basically, it's telling you how likely it is for a particle to occupy a state given a certain temperature. So if we remember the Boltzmann distribution, it basically said that particles are more likely to be in lower energy states, and it was kind of governed by this sort of exponential function right there. But the Bose-Einstein distribution is very similar. So if we plot the Bose-Einstein distribution, it's very similar for large energies, but at small energies it differs somewhat. So the two curves converge at large energies, but for small energies you find that there is a significant difference in the average occupancy right there. And this is coming from the quantum mechanical effect that happen when you get into this regime of low temperatures and densities that are on the order of the thermal wavelength, which we talked a little bit about in the previous video. So I first want to ask the question, what is the total particle number determined by? So if we imagine like our very classic kind of box of gas, in this case it'll be a box of bosons. So I'm just going to draw a box which has a certain number of bosons. Now, if we remember our thermodynamic properties, we know that the box has a temperature T, and it also has a certain chemical potential because we're in the grand canonical ensemble where particles are free to flow in and out. It has a chemical potential of mu right there. So what determines this total number of particles? Well, we can calculate the total number of particles by simply summing over the average occupancy of each state. So if we go through all of our states right here, which I've drawn as kind of like rungs on a ladder, then we can just sum up the total number of particles on each state. So we can see there's 1 in there, there's 2 in there. We've done this a few times before. So we can just obtain the total number of particles just by summing up over all the states, which I'm just going to call K, the average number of particles in each state. Of course, it's going to fluctuate because, of course, no particle is going to stay on its particular state. It's not going to be in the same state all the time, but each state is going to have an average number of particles occupying it. And so if we sum over all these average particle occupancies, then we're going to obtain the total number of particles in the gas. So what are we going to do? Well, we're going to sum over the states. And what is this average occupancy? Well, that's just the Bose-Einstein distribution, 1 over e to the minus epsilon minus mu over kBt minus 1. Now, we're talking about this a lot in theory, but in reality, are we really going to sit here and count the number of particles in each ladder? Because that is, let's face it, that's impossible. So we're going to have to do some kind of approximation. Now, what we often do, we did this in the density of states derivation, but what we are going to do with this is we are going to convert this, rather than being a sum over discrete states, we are going to convert this into an integral over sort of a continuous set of states. Now, this is an approximation because obviously states are not technically continuous, they are discrete because of quantum mechanics. That's basically what quantum mechanics is saying. You can only have discrete energy levels. But since there is so many, you might as well treat them as continuous. It's like having a sort of hair comb which the blades are so fine together that it might as well just be a smooth metal, basically. That's kind of a good analogy of looking at it. So we're going to be doing an integral over all of the states, but of course when we derive the density of states, we converted from integrating over states to integrating over energies, which is much easier to do. So what we're actually going to do is we're going to integrate over energies. So we're going to go from 0 to potentially infinite energies. And we're going to integrate this function right here. Of course, we have to also include the density of states function because there are going to be multiple states at the same energy. So this will be like, you know, discrete example like this. So we obviously have to count all 4 states right here. So there's our density of states, and then we're going to multiply this by the Bose Einstein distribution right here. And then this is all going to be integrated with respect to epsilon. So this is our integral right here. This is going to help us work out the total number of particles in this box. In this case, it's going to be the total number of bosons. This is a general formula that you can use to work out the total number of bosons in a system. This is generally how you do it. You multiply density of states by Bose distribution and then integrate that all over energies. So what did we say the density of states was? Well, when we derived the density of states, we had to use the dispersion relation, which basically is the relationship between energy and momentum. Now, this is of course going to be different depending on what type of bosons you're going to be working with. So for light, if you remember, the dispersion relation was epsilon is equal to momentum simply multiplied by the speed of light. That was a linear dispersion. But for massive particles, which is particles that have mass, then the dispersion relation was p squared over 2m, which is literally just half mv squared, but written in terms of momentum. Now, in this case, we're going to be dealing with bosons which have a mass. And this is typically what makes up the Bose Einstein condensates. Now, it's interesting to consider at this point, not all bosons can have the ability to form a Bose Einstein condensate. Now, this is a mathematical thing. When we actually reach the part of the derivation which determines whether a particle can become a Bose Einstein condensate, then I will point it out. But for now, just note that massive particles, we are going to be using the dispersion relation for massive particles, which is this right here. So what was our density of states? If we remember back to the video I did on density of states, then we found that the density of states for particles which had a mass was something a bit like this. You would have your energy along here, and then the density of states would scale proportionally to the square root of the energy. So there are a whole bunch of other constants that were before in the prefactor, but basically the density of states would scale proportionally to the square root of energy. And for our purposes, that's kind of all that matters. We don't really care about all these constants a huge amount. We're only interested in pretty much how the density of states scales with energy. So what I'm going to write is I'm going to write that this integral right here, I'll write it over here. So this is going to be equal to the density of states, which we said was proportional to the square root of energy. So what we're going to write is we're going to write a bunch of constants, which is basically all these constants, which includes mass, h bar, pi, or whatever. And we also said that the density of states includes a volume term as well. Now, normally the volume term would be treated as a constant. However, with Bose Einstein condensation, we're going to be talking about densities a lot. So we're actually going to write the volume term right here. And then we're going to multiply this, of course, by the square root of epsilon. So that is basically our density of states term right here. In fact, for more explicitly, I'll write out what the density of states actually is. So it's C multiplied by V multiplied by root epsilon. And C I have defined to be 4 pi root 2 mass to the 3/2 over 2 pi h bar cubed. So this is the density of states for particles which had mass, and basically the way I've written it is I've factored all the constants into this term C apart from the volume, which normally we would consider a constant. Normally we're only interested in how it compares with how it scales with energy, but for this particular case we're leaving volume in there. So that's the density of states, and then we're going to multiply this by the Bose Einstein distribution. So E minus mu over kBt minus 1 integrated with respect to energy. Now, this isn't a hugely easy integral to perform right away, so we need to think a little bit first before we actually perform this integral. Now, the most problematic thing is this chemical potential mu right here. Now, Bose Einstein condensation basically only happens when the chemical potential reaches as close to zero as it can possibly get. We talked a little bit about how in the dilute gas limit the chemical potential was very, very, very far away from zero. The further away from the chemical potential is to being from the thermal energy, then the more like a classical gas it behaves. But we're not in the classical regime, we're in the quantum regime. So we are going to consider the case where the chemical potential becomes very, very close to zero, asymptotically close to zero. So let me just draw a graph of this real quick, just to show you what I mean. So chemical potential, which of course we said was negative, so I'm going to draw a kind of reversed axis right here. So here's our chemical potential, and then here's our total number of particles. Now, for a gas, it's of course sort of equal to e to the minus mu, or e to the plus mu over kBt, because of course mu is in itself negative. So we're going to get this reverse exponential curve right here. Now, this was, of course, in the classical regime, but what's going to happen when mu gets very, very close to zero? Then we want to find out what happens at this critical point right here. What happens when mu, the chemical potential, equals zero? So this is basically what happens when we start getting the effects of Bose Einstein condensation. So basically, the condition for Bose Einstein condensation is that mu is equal to zero. So that's the thing you have to bear in mind. Mu equals zero. So what we're going to now do is we're going to calculate the total number of particles in a box in this specific case of mu being equal to zero. And just to signify that this is a different quantity, I'm going to call this quantity n star. Now n before, just for comparison, was the total amount of particles in a box as a function of chemical potential and temperature. But now we're fixing chemical potential equal to zero. So now we are going to try and find out the total number of particles in the box for 0 chemical potential. So let's just go ahead and rewrite what we wrote. So we have CV, which are actually constants, so I'm going to factor them out the front of the integral, times the integral between 0 and infinity of the square root of epsilon, all divided by e to the epsilon minus mu, which is what we had before, but of course mu is 0, so it's going to be minus 0, over kBt minus 1 d epsilon. So now we have this integral which will enable us to find out the total number of particles in this box. So what we're going to do is we're going to have a look at this integral and we're going to see what happens to this integral near the limits. Now this is a trick that often mathematicians like to use. You inspect the value of the integral near both the lower limit and the upper limit. And if it looks like it's not diverging to infinity, then basically that tells you that you have that this is mathematically sound or okay. In our case, it tells us that we can get Bose Einstein condensation. What I'm going to do is I'm going to make the substitution that x is equal to epsilon over kBt. I will do a substitution very similar to this a lot of times. It's basically just a trick to kind of make the integral and the maths a little bit easier. And if we take a differential, you can see that dx is equal to d epsilon over kBt. So that's our substitution right there. And now we're just going to go ahead and replace all the epsilons with x's right there. So n star is equal to cv multiplied by the integral, again between 0 and infinity, because x scales linearly with epsilon. So if epsilon goes between 0 and infinity, x will also go between 0 and infinity. We're going to have, instead of root epsilon, we're going to have kBt x. Instead of writing the square root, I'm just going to write it as the power of half, all divided by e to the x minus 1. And instead of d epsilon, we're going to have kBt dx. And just to tidy it up a little bit, we're going to get cv, and we're going to get these kBt terms, which were all constants, coming out the front of the integral. And we can see that there's a kBt to the half right there and a kBt just as it is. So we're going to get kBt to the power of 3/2 out the front of the integral. And then I'm going to integrate between 0 and infinity, root x, because that's all that's left of this term. Everything else has come out the front. Divided by e to the x minus 1, integrated with respect to x. So now let's have a look at this integral right here. Now that we've got it in a better form, we can have a look at this integral and see what's happening at the limiting cases. So as x goes to infinity, what's going to happen to this integral? Well, whenever you have an exponential term, this is by far the most kind of domineering part of any mathematical expression, because e, like if you graph e, then you get this very, very upward slope. Of course, you're going to have other functions like, x squared or, x to the half. They're also going to kind of play a part, but e to the x is the most domineering function. You can think of that as the thing that it pretty much determines what happens in the limiting cases. It will kind of override anything else. So as x tends to infinity, e to the x is going to get very, 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 very big. And so this 1, I think, like I said in the last video, isn't really going to matter. So basically, root x over e to the x minus 1, this will basically become root x over e to the x for large x. And that is equal to root x equal e to the minus x, just turning the exponential on its head. So what's going to happen to this integral, root x e to the minus x? Well, if x is large, then root x will be large, sure, but what did I say before? The domineering term of any product of functions is anything inside the exponent. Now for large x, e to the minus a very large number is basically 0. So it's as close to 0 as you can get. And what that basically means is that for large x, when x gets really, really high, it becomes, first of all, this basically becomes this. And you can clearly see that when x is large, then you can see that this whole thing will basically become 0 for large x. So this is kind of the upper limiting case. So that's kind of what we want. This is good. This means that you won't find that the number of particles in the box will just increase drastically. It will converge to a certain point. So mathematically, this is fine. What about the other case? What about when x is very close to 0? So as x is small, then what happens to this equation right here? So you have root x over e to the x minus 1. Well, what we do a lot in maths is that if x is small, if the argument is small, what we can do is we can do an expansion. We can use the Taylor expansion just to approximate what it will be like for very small arguments. So e to the x for small x is approximately equal to the first order 1 plus x right there. Technically it will go on forever. It will go on, there'll be an x squared term, there'll be an x cubed term, so on and so forth. But because x is so small, it doesn't matter about these. Like, we can just look at the first two, as that's kind of the only ones that are important for this. If e to the x is about 1 plus x, then we can see that e to the x minus 1 is basically about the same as x. So if we just subtract 1 from both sides, because of course these terms are so small, I'm going to rub them out because they are so small. E to the x minus 1 is basically x. So what happens to our integral here? Well, this equation, root x over e to the x minus 1, what we said was that e to the x minus 1 is about x, so this will become root x over x, which is equal to 1 over root x. And again, what's going to happen when this is small? So again, when x is small, then you have 1 over root x, which when you integrate over from 0 to infinity, then you can find that that is indeed a convergent integral. So this is fine, basically. This integral is completely fine. And let's just go ahead and rewrite it right there. So just a quick note, if this test doesn't work, if you make x small and large, for either both cases, x doesn't converge, then you have a problem right there. So this is like a little mathematical trick. And if it doesn't pass, then it's not ideal, and then you can't get Bose Einstein condensation. So there is our integral. Now this quantity right here, we've just shown that they are both convergent at both limits, and therefore this is literally just a number. Like there's nothing physicsy going on right here. There's just a bunch of terms inside an integral. Like this is just a literal number right there. So what is this number? Well, all this right here is basically about 2.3. Like that's all that is. It's just a fancy way of writing 2.3, I guess. And so let's just go ahead and rewrite this in its much more simplistic form. So it's 2.3 multiplied by CV times KBT to the power 3 over 2. So that's n star. So let's just think about what we have actually calculated for a moment. We have just shown that if we have a box and then we fill up our box full of bosons, we have just shown that there is literally just a number, like this number right here, this is fixed. This doesn't really necessarily change. This is just a number of particles in a box of a certain volume at a certain temperature. And this is when we assume that the chemical potential is zero. So there is a slight problem here. This might look all right on the surface, but actually there is a slight problem with this analysis. This is basically saying that at a certain temperature, you can't add any more particles to this box. So that's a bit weird. Like, you know, imagine trying to add a particle to the box and just having it being like, no, you can't do this. Like, that's a bit weird, right? This is kind of what it's showing. You can only have this maximum number of particles in a box, and that would kind of imply that if you tried to add another one, then there would just be some kind of weird force which would try and repel you from adding another particle to this box right here. Because remember, we are in the grand ensemble, particles can flow in or out. It shouldn't be so that there is just this number, this constant number that is a maximum number of particles in the box. Conversely, this would also mean that if we were to lower the temperature of this box right here, so say we cooled the box down, does this mean that like particles will gradually start disappearing from this box, like mysteriously vanishing from thin air? Like, that makes no sense at all. Like, that is really, really weird. So what is going on here? This is some kind of a paradox that we need to kind of explain, because this is very strange. So the way we actually get around this paradox is to go back to our original graph that we had, looking at the dispersion relation for our types of particles that we are considering. So if we go ahead and plot that right there, then we get our parabola, just like we had before, our p squared over 2m parabola. So this is energy as a function of momentum. And if you remember, the way in which we calculated this n star right here was just by summing over the different states and then multiplying by how many states, which is obviously the density of states thing. So just summing up all these individual ones. We also did the ones for the negatives. And yeah, we just kind of went up this like sort of infinite load of states. But there's one state that we didn't actually consider. It's this one right in the middle, right here. The density of states function does not accommodate for this right here. It only deals for states that are above zero, but it doesn't actually technically describe what's going on right at the center point right here. And basically what's going on is, rather than there being this kind of fixed number, of course the same number of particles will still be there from when you start sort of cooling the gas. So the thing that's happening is that particles are basically starting to all pile up in this state right here. So all the extra ones, all of the extra particles that are not n star, so you have n star particles that are not sort of there, but then you have all these extra ones right here. All these extra ones are all piling up in the middle, all in this kind of p equals 0 dispersion curve right here. Now what's going to happen when we start piling up loads and loads and loads of these particles? There's going to be way more of these particles in this part, all in this kind of p equals 0 part of the dispersion curve, than all of these right here. There's going to be way, way, way more. And eventually you're going to start having ridiculously high numbers. And that right there is what the Bose Einstein condensation is. It's basically all these particles in the ground state of this dispersion curve. So they've all got p equals 0. They're all their wave functions are kind of infinitely spread out, or not technically infinitely, but like really, really spread out throughout all of space. and they're just all kind of there. So what is it that we're talking about exactly? We're just kind of talking this kind of ghostly kind of haze that's just around, made out of these particles that are in the ground state. So it's this really weird idea, like they're just all kind of floating around, I guess, but they've got zero energy, and their position is not very well described because their momentum is zero. So their position, according to the thermal wavelength, lambda equals h over p, like their wavelength is just spread out, so we can't accurately determine where they are. And that is what it is. It's crazy that this is even a thing. That is what a Bose Einstein condensate actually is. It's an infinite load of plane waves just hovering around. And you can get some really cool effects from the Bose Einstein condensation. And we're going to talk about just a few in right a moment. But what I just maybe wanted to touch upon, this kind of transition between Bose Einstein condensate, so from normal gas, from like normal gas behavior, going to Bose Einstein condensation. This is an example of something that's a little bit more general in physics and something I'm going to hopefully touch upon. This is an example of a phase transition. And what this is, a phase transition is basically something where you have this one kind of state of a system, this kind of normal state. If we reduce temperature or anything else, then you end up in this kind of different state right here, like very suddenly. There's no real kind of smooth transition. It's a very quick kind of jump. And in fact, if we just draw a graph of what basically temperature and sort of the number of particles that appear in like the Bose Einstein condensate. So this will be like n minus n star, where n is the total number of particles in the gas, and n star is this number that is not in the condensate. This is the number that's kind of being occupied in this part of the graph. So if we plot that, then as we cool the temperature, of course we have nothing for ages and ages and ages, and then suddenly at this critical temperature, we get this jump where you suddenly start getting particles in the condensate right here. So like particles just start piling up at this very like sudden critical temperature, which is very weird because not a lot of things in physics really behave like that suddenly, but that is what is actually happening. You're suddenly getting this jump from nothing to basically Bose Einstein condensation at this critical temperature. So this is what I just wanted to touch upon, is that it's a more general example of a phase transition. So one last thing about Bose Einstein condensates is that not all of them, but some of them show a phenomenon called superfluidity. Now, superfluidity is really, really cool. It's almost ghost-like. Imagine this kind of ghostly phantom haze that is able to kind of defy gravity and just sort of not quite know where in space it is. That's basically what superfluidity is, and it's really, really cool. Most Bose-Einstein's condensates show superfluidity. Basically, the physical thing that defines it is with the viscosity of the fluid, mu, is equal to 0. There is no viscous force on this fluid. It's basically free to sort of run along a surface infinitely without being slowed down. Because in a normal fluid, there are shear forces, which is basically viscosity. They are what slows the fluid down. That's what kind of defines a fluid. Whereas a superfluid, the viscosity is just flat out 0. So just to illustrate what I mean, I'm gonna draw sort of a jug. So here's our jug, if you like. And we're gonna fill this jug up with some Bose Einstein condensate. And obviously this jug is kind of sat on like a table, and you know, it might be sort of in a room or something right there. Then the thing that's going to happen once you put this Bose Einstein condensate in a jug, then it will actually kind of basically run up the walls and then just kind of like basically just go all the way around the walls just like this, and then it will just sort of flow to coat the walls as if there's no force stopping it, which there isn't. There is no force stopping this Bose Einstein condensate from flowing all the way around the table and then just going all the way along the floor and then up the walls and then up on the ceiling right there. It's really cool. And that is basically what superfluidity is. Basically no force is stopping the fluid from going across the surface. The condition that a Bose Einstein condensate needs to have for it to be superfluid is basically known as the Landau criterion. And what the Landau criterion says is that there is a critical velocity, Vc, below which a fluid will move like a superfluid. And it's basically defined by the minimum of the energy divided by the momentum right there. That's all a little bit vague. I'll just elaborate on what that means. For a normal fluid, so like this one we've just been considering right here, it actually turns out that you can't have superfluidity. Because if we plot the dispersion curve, then what's the minimum of this kind of ratio right here? Well, the minimum Vp is going to be here. And if we divide by p, it's not going to really make any difference. So it's just going to be p squared over 2m, all divided by p, which is just p over 2m. And the minimum of that is still 0 right there. Since the critical velocity below which has to be satisfied, and since in this case there is no critical velocity, it's just 0, then in this case, with this dispersion relation, you can't actually have a superfluid. But I'll show you an example of a dispersion curve which can be superfluid. So say we have this graph right here that goes something like this. So we have this kind of minimum right here, and if you analyze the curve, then you take the ratio of EP over P at each point, then you'll find that at this point right here, there is a minimum in that. And this minimum is non-zero, like this velocity minimum. You can kind of see from the graph it's non-zero. And yeah, this right here is the critical velocity. And anything below this velocity, which you'd have to know the exact equation of this curve, but anything below this velocity, you will have superfluid behavior. Above the velocity, then it just behaves like a normal fluid. But below this velocity, then you basically get superfluid behavior. And yeah, it's really cool. One other way to look at it is by considering, say you've got this like little bowl, and inside this bowl you have a Bose Einstein condensate, and then you have a spoon which you dump into the bowl right there. Now, what do you normally expect with a fluid? Well, you normally expect, as you move the spoon through the bowl, the fluid to kind of drag along with it, and the fluid to sort of, create some kind of like disturbance. There's going to be some sort of shear force. But of course, with a superfluid, then there is no shear forces. There is 0. And what you'll actually find is when you move the spoon through, then you'll find that the fluid won't change, which is a very ghostly kind of weird thing to experience. Like if you sort of imagine moving something through what appears to be a fluid, then there will be no sort of disturbance from in the fluid up till the critical velocity, after which, yes, you will experience turbulence and flow. So basically, what is the maximum velocity you have to drag this spoon through in order to not experience that? Well, that's Vc, that's the critical velocity. And that's just another way of looking at basically what that means. And that is basically superfluidity in a nutshell. So yeah, I hope that was an interesting video, guys. I find this stuff really, really cool. I think it's amazing that there's a whole nother state of matter that none of us are really that aware of. and it can kind of sometimes go up walls, which is amazing and very, very weird. Just more of that quantum weirdness, I suppose. So yeah, in the next video, we're going to be having a look at fermions. We've had a look at bosons, and now we're going to have a look at fermions, and we're going to be looking at how fermions are a very good model to describe most metals, and how you can actually do things like a lot of the solid state physics and semiconductor physics kind of come from a lot of the theory that I'm about to go into right here. It is quite complicated. I certainly struggled with it, but I'll hopefully do my best to explain it in a way that's as clear as possible. So yeah, see you guys then.